I wanted to bring to your attention some important thoughts about circular motion, and I thought I would take you back to the example I used, or the illustration I used, in order to establish some other key facts in my second video, I think, on circular motion. Let's consider a stone or a mass on a string hanging vertically down. So at that point, there is no acceleration. You have the weight acting down. You have the tension in the string acting up. Now, if I pulled it to one side, imagine it's pivoted in the middle here. If I was to pull it to one side, nice and high, and let it go, at the point that I let it go, there are only two forces acting on it. We're ignoring air resistance, of course. We have the tension in the string, and we have the weight. But now, of course, my stone or mass, whatever it is going to perform at least part of a circle. So it is performing circular motion, and therefore there is a resultant force causing that. But the resultant force is the resultant of the two forces that were acting before. It's not a new force. The centripetal force isn't a new one. It's the resultant of the forces that were there already. There's often a temptation to introduce centripetal force as some additional force to the problem once things start moving in circles, and it's not true. I have, of course, applied a force to get the stone up here, but that's irrelevant in the sense that when I let go, that force is gone, and then my object begins to perform its circular, or in this illustration, semicircular motion. So here, the tension equals the weight as the stone hangs vertically downwards. I know this is labelled differently, but we're talking about a slightly different circumstance here. We're talking about the string hanging vertically downwards, stationary. So we have the weight acting vertically down, we have the tension acting vertically up. These two forces on the stone or mass or whatever are equal and opposite. There is no acceleration. Once I take it up to here and let it go, then it is performing circular motion. So there is an acceleration towards the center of the circle, and so there is a resultant force, which means the tension must be changing. Now, that's maybe self-evident in this example because the tension here doesn't have to be the same as the tension here, because the tension here is supporting the weight, whereas it isn't supporting the weight here. So you can see that the centripetal force is the resultant of the forces that were acting before, the tension and the weight, and not some magical additional force that pops up when things start moving in circles.